Okay, so here's a quick review of some of the things that we've done previously and which are going to be relevant to today's lecture as well. So we've talked about systems in general, and like I said, there were two important properties. One of them was linearity, the other one was time invariance. Okay, and what we're going to be focusing on from here on for about 2 or 3 lectures is going to be focused on linear and time invariant systems. So there are many systems that you're going to come across in practice, which are linear as well as time invariant. And these are an extremely important class of systems, not only because they're very mathematically tractable. I mean, it's very easy to characterize the performance, characterize their behavior, but also many systems that you come across in practice are in fact linear and time invariant as well. And in short, when a system is both linear as well as in time variant, so we use the acronym LTI. LTI stands for linear and time invariance. So as you see on the screen here as well. So LTI systems are linear and time invariant systems. So just as a recall, a review, what is time invariance? We've defined this in the previous lecture. We said, KG, if the output of a system is if input is x of t and the output that you get from this x of t is y of t, a system is going to be time invariant when any shift in the input results in the same shift in the output, right? And that is another way of saying, a mathematical way of saying that the behavior of the system is invariant to time, right? Does not change with time, right? So mathematically speaking, this is the definition that you see on your screen. So x of t results in y of t, then x of t minus t naught is going to result in y of t minus t naught for all time t naught on the real number line. Okay, so that's the first property that's important. The other property that's important is linearity, right? And we say that linearity का मतलब क्या है कि if I scale the input by a constant, the output is also scaled by the same constant, right? So that's one. The other is if I add two inputs, the output that I'm going to get is going to be equal to the output, which is a sum of two outputs, with the individual outputs being those outputs corresponding to the individual inputs, right? So if x1 results in y1 and x2 results in y2, then x1 plus x2 is going to result in an output which is equal to y1 plus y2, okay? And more generally, this is going to hold. If I have any linear combination at the input, the output is going to be the same linear combination with the constituents output as you see on the screen, right? So if xk results in yk, then a summation over k hk, where hk is a constant times sk, is xk is going to result in an output with a summation hk times yk. Okay, so this is time invariance and linearity. So these are the two important properties. All systems that we'll be talking about in this chapter are going to be characterized by these properties, linearity and time invariance. Okay. What I also want to quickly review is the sampling property of a unit impulse, right? So because this is going to be extremely important as far as we're concerned, as far as this lecture is concerned. So property number A, as you see on screen, is if I multiply x of t with delta of t minus t naught, a shifted impulse residing at time t equals t naught, what is the output going to be? So what is the output here? What is the output here? So it's going to help me. Ji Hassan.
Sir, it will be x of t naught.
Yeah.
The value of at t naught, and then same delta function.
Excellent. Delta right? So times delta t minus t naught. Okay. And this is the sampling property. So all the multiplication with the delta does as a function of time, कि x of t को t naught पे sample कर लेता है, and then you're left with that amplitude of an impulse residing once again at t naught. Okay. Hassan, what about part B? I mean, what is this going to be equal to?
So in this case, we will just get x of t naught.
X of t naught. And the reason is because if I just apply property number A, so this is going to be integral from minus infinity to infinity, x of t naught times delta t minus t naught. And then as far as time is concerned, x of t naught is nothing but a constant, right? As far as the integral is concerned, right? So this is minus infinity to plus infinity, delta t minus t naught dt. And this integral area under the curve is always 1. That's a property of the unit impulse function. So therefore, this is equal to x of t naught. Okay. Now, if you understand this concept, let me try to quiz you a little bit more. I mean, with some hanky-panky in the change of variables, right? So what is that change of variables? So let me ask you another question here, which is an exercise, if you will. Okay. Right. So if I ask you, Kiar, what is this equal, this integral equal to, where this is x of tau and delta tau minus t d tau. What is this equal to? Gzen, what do you think?
So actually, I get really confused जब भी ये tau आता है because like I don't know why do you even do this. So like sir, this should actually t minus t naught actually meant कि we have shifted the graph आगे. So if we look at this, to minus t plus tau means that we have shifted it पीछे और हमने उसको y axis पे transform भी कर दिया if I am not wrong.
See, I
So
mean, what is what is the difference between the equation number B that you see above and this equation? There's no difference whatsoever.
yes sir, yes sir.
It's
Very
only
clear.
different variables that I'm using. I mean, tau ki jagah, instead of t, I'm just using tau. That's just a name of the variable. Your understanding, once again, I mean, this is the point I actually wanted to make here. Your understanding should not be a function of this variable name, right? All I've done is I've replaced t with tau and t naught
Yes, sir.
with t. That's all I've done. Other than
Yes,
that,
sir.
the function or the integral exactly is what we had done before. Okay? So that's
So
why
we shouldn't actually assume कि जो T naught है वो हमेशा shift show कर रहा होता है मतलब आप उसको किसी भी notation से
so
replace कर
हमेशा
सकते
नहीं कर रहा होता, right? So and that's how I'm going to test you, and that's, I mean, your understanding should go beyond the use of variables, right? Because in many textbooks that you're going to come across, I mean, every textbook uses a different variable. Okay,
Yes, sir.
and online resources are going to use different variables as well. Okay, so your understanding should be at a level where it is not dependent on what variable names you use. Okay, so that's the point I want to make. Hassan Shabir, you raised your hand as well. So do you have an answer to this, or?
Here I had the answer to this.
Gigi, please go ahead.
It's x of t.
X of t, and as Mustafa says in the chat window as well, the answer is x of t, right? And you see, the difference here is what? The difference here is, okay, I'm integrating over the variable tau, right? And as far as tau is concerned, delta of tau minus t is actually as a function of tau. So if this is my x-axis where this is tau, my delta now resides at tau equals t, right? And there's an x of tau here as well, as where tau is the independent variable. And when I multiply those two together and integrate it out, I'm just going to get the value of x at time tau equals t, right? So there's just a change or in perspective here, right? Okay, Ji Hamza, go ahead. Question?
सर वो बस आपने आंसर कर दिया।
Okay.
वो टी मुझे समझ नहीं आई थी कि ये कांस्टेंट है या
Good,
varying
right?
है।
So as far as this integral is concerned, right? As far as this integral is concerned, t is independent of tau, so therefore t is a constant as far as the integral is concerned. Okay, but this entire thing, Hamza, this entire thing on the left, what is this a function of? This is not a function of t. Oh, sorry, this is not a function of tau, because tau is you're integrating over. Okay, at the end of the day is going to be a function of t, because for t equals 2 is going to get a different value. For t equals 3, you're going to get a different value. For t equals 4, you're going to get a different value. So as you keep on changing t, this integral evaluation is going to keep on changing as well. Does that make sense, Hamza?
जी सर वो लिमिट्स हैं ही टी के फॉर्म में,
Exactly.
में नहीं है।
Right. So the left hand side is actually a function of t now as a variable t. Okay. So so this is what the integral is equal to. Okay. Now let me add another level on top of it, just to make this is a perfection ki taraf, right? So a perfection of understanding, right? Which is let me minus infinity to infinity. This is x of tau. And then I have here delta t minus tau, d tau. So what do you think this is going to be equal to? Any guesses, any ideas? So, I mean, what's the difference between C and D? The only difference is instead of delta tau minus t, I now have delta t minus tau. But the integral is still over tau. The integral is still over tau. So what is the output here going to be? What do you think? So my question therefore is...
So the output should remain the same.
Should remain the same. Why is that?
Because से जब आप उसको minus tau करते हैं, you're actually reflecting it over the y-axis ना.
Yeah.
तो हमने ये assignment में भी किया था कि but the area under the graph should remain the same. In my opinion, like.
Okay, good.
If
good, right? So, I mean, so for this, you need to first of all figure out what delta t minus tau is going to look like with tau as the independent variable, right? And you can verify, and it should be clear, that this is nothing but the same delta which resides at t, right? So delta of t and delta of minus t are exactly the same. Or another way you can think about this is that there's going to be impulse. There's going to be an impulse when this argument is equal to 0. So impulse residing at, or impulse where this argument equals 0, t minus tau equals 0, which implies tau equals t. So this is where the impulse is going to reside at t equals tau. Okay, or tau equals t, which is exactly the same thing. Right, so this is still going to be x of t, right? Exactly the same thing as Zan, you correctly point out. Okay, and some people, Hassan as well, say that. Hassan, why do you say minus x of t? There were other answers as well, minus x or minus t. So can I try to scratch your brains, Hassan? Can we? Got it now. All right. Okay, good. Okay. So let me, so this conclusion that we have is the following. Okay. X of t, any arbitrary signal x of t is equal to minus infinity to infinity x of tau delta t minus tau. So this is a conclusion that we've made here, right? So let me box this here. Okay, and this is called the sifting property.
Excuse me, sir.
Yeah.
सर जस्ट टू क्लैरिफाई सर अगर यहाँ पर हम लोग जैसे असाइनमेंट में था कि जो हमारे पास अगर हम लोग वो हॉरिजॉन्टल शिफ्ट पहले करें और रिप्लेस बाद में करें और लाइक वो चीज़ करें तो सर उससे तो फर्क तो नहीं पड़ेगा लाइक फिर भी सेम ही आएगा ना बिकॉज द ग्राफ शुड वुड बी द सेम तो एरिया ऑन द ग्राफ भी सेम ही रहेगा
एग्जैक्टली सो इट वुड स्टे द सेम
बट सर अगर कोई ऐसी ट्रांसफॉर्मेशन होती है जिससे हमारा आधा ग्राफ एक्सिस के ऊपर रहता है आधा नीचे चला जाता है तो उस केस में तो फिर इंटीग्रल की वैल्यू फर्क हो जाएगी ना लाइक हमारी ग्राफ की शेप कुछ इस तरह की बन रही है लाइक आई कैन एक्चुअली इमेजिन अ सिनेरियो बट लाइक कोई ऐसी ग्राफ की शेप हो जिस पे जब मैं ये ट्रांसफॉर्मेशन अप्लाई करूं तो वो आधा एक्सिस के नीचे चला जाए और आधा ऊपर रह जाए तो उस केस में जब मैं एरिया निकालूं
what do you mean going above the axis and below the axis?
Sir, actually, there is this line as जो t वाली time की line है that represents the x-axis ना. So when we calculate the area integral लेते हैं हम लोग, so we are actually calculating the area between the graph and that line जो t वाली है. So what if there is some kind of transformation which I can't actually think of अभी कि कौन सी होगी, but जिसकी वजह से जब मैं graph को shift करता हूँ, then half of the graph or some part of the graph falls below the t-axis.
No, so only shifting on the time axis will never result in that. So you would have to do some scaling on the y-axis.
Yeah. Okay.
For that to happen, what you're saying. Okay.
Okay.
Right?
Same. Thank you, sir.
On the x-axis you're shifting time domain में transformation, time axis
नहीं
पे,
होगा.
I mean that won't happen.
Okay.
Okay. So this is what you see in the box here is called the sifting property. Now let's try to see what it actually means, right? So can somebody try to interpret here? I mean, when you look at this equation, right, where we say x of t, any signal x of t is going to be equal to an integral minus infinity to plus infinity x of tau and delta t minus tau d tau. I mean, क्या ज़हन में क्या आता है इससे? And I'm going to try to intuitively explain what this means, but let's see. Hassan?
So the way I see it is that the integral is basically scanning from minus infinity to infinity. And as it's scanning throughout the whole thing, my x tau or delta function they're multiplying with each other.
Yes.
And because the delta function is 0 everywhere except at tau equals t,
yeah.
So as it's scanning through the whole thing, वो हर जगह 0 0 0 दे रहा है until it reaches t equals tau.
Okay, good.
वहाँ पे the only thing it can multiply with is x of t,
Yeah.
which is what it gives you, and then it continues and just gives you zeros everywhere else.
Okay, excellent, excellent. Hassan ne bolia, Masna, you had your hand raised as well, I think.
Sir, I had the same answer.
The same answer. Okay. Let me. So what you're saying is exactly, which is what you mentioned, Hassan, is actually the sampling property of the delta signal anyway, right? I think that's what you were referring to in an essence, right? So kg delta of t minus tau only resides at tau equals t, so that's where you sample it and that becomes x of t. Let me give you another interpretation, and that interpretation I have is this integral is a scanning in the sense this is actually a sum, right? So integral can be thought of as a sum, and you're summing or scanning from minus infinity to plus infinity, and you're just delta t minus tau, for example, delta t minus 1 and delta t minus 0 or delta t plus 1, all of these are impulses from minus infinity to plus infinity, and you're just summing them up somehow. Okay? In order to visualize this further, let's try to see graphically what this represents. Okay, so here's some intuition behind the sifting property. And your textbook actually starts out with this. I've gone the other way around, just because the way we've done it in the previous lectures, right? So let's say there's an arbitrary signal x of t, okay? And let's just, okay. So let's say this is the time axis, and there's some arbitrary signal which looks like this. And this is, let's say, time 0. Now, in order to approximate this signal, one of the things I can do here is just approximate this as a staircase. So let me say here, this is a rectangular pulse, right, which has a magnitude equal to or a height equal to x of 0, right? And this pulse is of duration capital delta seconds. Okay? And then there's another rectangular pulse which has a duration of still a delta second, so that this is 2 delta. Okay? What is the height here going to be? So this height here is going to be x of delta. Okay, you get the point? So what I'm doing is I'm coming up with a staircase approximation to this continuous signal, right? Approximating it by boxes, right? And so on and so forth. So let me draw a few more. And this is another box, right? Or a pulse, which is once again of duration capital delta seconds. And the height here is going to be x of 2 delta, and so on and so forth. And similarly in the negative axis here as well, right? So this is another box. This is minus delta, and the height here is x of minus delta. Okay, and oops, this is another approximation. So this is minus 2 delta. And the height here is x of minus 2 delta. And this goes on. Right, so the approximation that I've come up with is that like the staircase approximation. Okay, now if I were to write the staircase approximation mathematically, how would I do that? For that, I will use the delta approximation that we've used, that we defined earlier, right? So recall, okay, the approximate delta signal that we defined was following, was equal to 1 upon delta for 0 is less than t is less than delta, and a 0 otherwise, right? So which was essentially something of a pulse, right, of duration, capital delta seconds, and height 1 upon delta, right? Now, given all of this, can I come up with an approximation to x of t? How do I represent the staircase approximation? I mean, you see, the staircase approximation is actually nothing but a superposition of these boxes, which are time shifted and scaled by some constants, right? So I take a look and see the x of t is, so for that matter, let me say, Kiji, let me ask you this. What does this box or this brown box, if I were to write this mathematically in terms of the approximate deltas, what would this be equal to? What is this equal to?
X naught.
Sorry, who said this?
Sir, X naught.
X0.
X0.
But then there's a rectangular pulse, right? I mean, because if I say this is x of 0 as a function of time, that means it stays flat, right? So it's actually x of 0 times the approximation times delta, right? Why is this multiplied by delta? Because if I multiply this with delta, the height, so the height of this becomes equal to 1. Right? And then I multiplied by x of 0, so therefore the height becomes x of 0, right? But only in the duration from 0 to delta seconds. Okay? Acha. Using a similar methodology, what do you think this green signal is going to be equal to? Which starts at delta and ends at 2 delta. What is this going to be equal to? So there's a question in the chat box, why multiply by delta, right? So Talha, so this is multiplied by capital delta. Why? Because if I multiply this capital delta, with this approximation, right? What is the height of the pulse am I going to get? The height is going to be equal to 1. Right, because the original height was 1 upon delta. If I multiply it by the capital delta, the height is going to be equal to 1. And then when I multiply by x of 0, the height is going to be x of 0, right? So what I want is a pulse of height x of 0, right? So everything it clicks together. Talha, is that clear?
Okay, yeah, I get it.
Okay, thank you. All right, so what about this green thing? So Talha, I'm going to come back to you. What about this green thing? This green pulse? What is this equal to? Any ideas? Anybody else? Anyone ventures a guess?
Sir, can you repeat the question once?
So my question here is, if I give you this green this green pulse that you see, right, which is actually a rectangular pulse of height x of delta, but is not residing from 0 to capital delta seconds, but rather from capital delta to 2 delta seconds, right? So therefore, this is a shifted version. By how much? Capital delta seconds, right? So in terms of the time approximate or time transformations that we've talked about, what would this be? Ji Ibrahim.
Sir, I think इसका होगा कि x delta into
Yeah.
approximation of t minus delta into delta. इसका area
Excellent.
होगा.
Excellent. So this is t minus delta times delta. Good job, Ibrahim. Right. Right. So, and then similar, what about this white thing here? What about this white pulse? So somebody
Sir,
else?
वो भी सीधा से x of 2 delta into
Okay.
approximation of t minus 2 delta
Right.
into delta.
T minus 2 delta into delta. Excellent. Excellent. Right. Similarly, ये जो चीज है, this is x of minus delta times delta की approximation residing or shifted by plus delta seconds times capital delta. And this red pulse that you see is, all right, so this is not right. This here is x of minus 2 delta, delta t plus 2 delta times delta, right? And this goes on and on from minus infinity to plus infinity. So I can say I can approximate x of t, so this is an approximation here, as being equal to x of 0 times delta approximation of t times delta plus x of delta t minus capital delta times delta plus x of 2 delta. I mean, just shifted copy is adding up, and plus all the way up to infinity, right? It just keeps on going in the positive direction. And then there's something in the negative direction here as well, right? So this is x of minus delta. Okay. So x of minus delta t plus delta times delta, x of minus 2 delta t plus 2 delta times delta, and all the way up to minus infinity. So this is an approximation. Okay. Now, so this approximation is a sum of infinitely many square pulses, which are subsequently shifted every time by a capital delta seconds and scaled by the appropriate heights. Okay, and that gives you an approximation. Is there a mathematical way for me to, I mean, this looks like a very, very cumbersome or tedious expression. Can I represent this elegantly, more elegantly, with this approximation more elegantly, with just a small, okay, Talha says integration. So because I'm working with the approximation so far, okay, so I would rather use a summation here, okay, and then take the limit and then it will become an integration. So mathematically, I can say this is equal to k summation going from minus infinity to plus infinity. This is x of k delta times delta t minus k delta times capital delta, right? So it's just the equation that you see up top, right? Represented mathematically elegantly with this summation sign. With the summation sign, take all values of k from minus infinity to plus infinity and keep on adding them to the sum one by one, right? So it's like a for loop, if you will, right? Where the for loop goes for all indices of k, integer indices of k from minus infinity to plus infinity. So that's what this notation represents, this sigma notation represents, right? Which I'm sure you must all be familiar with, okay? And then as people point out in the chat window as well, so this is still an approximation. Why is this an approximation? Because you have this staircase approximation of the actual signal. this approximation becomes exact. When does this approximation become exact? Deepala? So what do you think? Limit, okay. Excellent. So this approximation becomes exact, as people point out. Approximation becomes exact when delta goes to 0, right? So therefore, I can say that x of t is actually equal to limit delta going to 0, k going from minus infinity to plus infinity, x of k delta t minus k delta times delta. And this is, as who said this? Ibrahim said, this is the Riemann sum, right? So this summation becomes an integral. So this is minus infinity to plus infinity. K times delta becomes, I'm going to denote that with tau. And the approximation of delta becomes exact as well as the limit goes. So this is delta t minus tau d tau. So take my word for this. This is what the integral is. This is what the summation is in that limit. Okay, which is nothing but the Riemann sum. Right? So this is an intuitive interpretation of what the sifting property is. This is exactly what the sifting property that we had earlier, right? But this now gives you an idea of what this represents. What this represents is any signal x of t can be represented as a linear combination of scaled and shifted impulses. Okay, so if you were to explain or you state this shifting property in words, you would say any signal, any continuous time signal x of t can be represented as a linear combination of scaled and time shifted unit impulses, right? So this is what the shifting property states, okay? Any questions here before I move? I mean, why is this important? We're going to see in a bit. Okay, we're going to build up on top of what we've done.
So can you explain this tau again?
Okay, so this is k. I've used a change of variables. K delta is tau. Okay.
Okay.
And this is nothing but the definition of integral, by the way. Right. I don't want to spend too much time here. Perhaps in some tutorial I can do that. So this is a Riemann sum basically, right? So Riemann sum is always this is the definition of Riemann sum, okay, which is an integral. Okay. So intuitively it's just a linear combination of deltas, which is a linear combination, a continuum in the sense. There's an integral there, not a finite sum. Okay. Now, given this property, let's try to apply this to some signal that we know of, right? So for instance, if I were to write down the unit step function as a linear combination of unit impulses, all I'll do is I take a u of t is equal to minus infinity to plus infinity x of tau is u of tau, sorry. Right, so this is u of tau, and this is delta t minus tau d tau. Okay, but u of tau I know is equal to 1 for all values of tau which are greater than 0, and therefore this integral reduces to 0 to infinity delta t minus tau d tau. So what we've concluded here is that a unit step can be represented in the following form: integral from 0 to infinity delta t minus tau d tau. Okay, so this is another description or relationship between a unit step and the unit impulse. Now here's a question for you. When we did unit step and unit impulse, the definition for you, or the relationship that we derived, was the following. So this is from minus infinity to t delta tau d tau. Right, so this is, I mean, this thing that you see in brown is what we derived when we were talking about the relationship between a unit step and unit impulses, right? But from using this shifting property, we have apparently have this equation number 1. And this is equation number 2. Right? How can you have two different definitions for the unit, two different expressions for the same thing? I mean, either one of them is incorrect or both are the same. What do you think? Ji Hassan. Shabir.
Sir, the brown one basically deals with all values. It depends on the value of t we're using. If
Yeah.
it's whether it will be less than 0 or greater than 0. If it's greater than 0, then it will automatically reduce to the blue equation.
Okay, but
so that's
I mean,
what.
for this to hold true, this should not only hold true for t is greater than 0, but also for t is less than 0. So one of the things you need to verify is that equation number 2 in brown, is that correct or not correct? And we've figured, we've done this. I mean, we've established the fact that equation number 2 is correct. Okay. We've also established the fact that equation number 1 is correct because we've derived this from very, very sound mathematical reasoning from all up above. So sifting property is an established fact. Okay. So number 1 is also correct. Number 2 is also correct. The only conclusion is that 1 and 2 are actually equivalent. They both are the same. That's the only conclusion. The next, therefore, job would be you have to prove they're the same or not, right? Or to prove how they're the same, right? Can you do some mathematical manipulation to show that equation number 1 is exactly the same as equation number 2, right? So can you manipulate equation number 1 to show that the equation number 1 is exactly the same as equation number 2? Anybody? किस तरह करेंगे? And that's simple calculus, by the way. Okay, so simple calculus is I will use a change of variables. So I'll work with 1. So prove that 1 is equivalent to 2, right? And what I'll do is let v equals t minus tau, right? Just make a change of variables, right? And I often say this, when in doubt, just apply a change of variables. I mean, this is going to solve a lot of your problems, right? So if v equals t minus tau, if that's a change of variable that I make, right, what happens to the limits, right? So when tau equals 0, v kya hota hai? V is t, right? And when tau equals infinity, v equals minus infinity, right? And dt is equal to what? D tau is equal to what? Or in other words, dv equals minus d tau, right? So if I just apply this change of variables to equation number 1, what I will get is, so from 1, u of t equals, so 0 changes to t and infinity changes to minus infinity, and this becomes delta of v times d tau becomes equal to minus dv. So this is dv and there's a minus sign here. So minus sign ko I can incorporate inside the limit. So this is from minus infinity to t delta of v times dv, right? Isn't this the same exactly as 2? And it is, right? Because there's the only difference is that, I mean, equation number 2, we have the name of the variable is tau. Here the name of the variable is v, but the names don't matter, right? So this is really minus infinity to v delta of tau d tau. And this indeed is the same as 2. Right? So everything is consistent, everything clicks together. And that's a big part of your understanding, or a big part of your learning process. I mean, it should be a big part of your learning process. You learn something and then you learn something new, right? You need to make sure that the things that you learned later fits into your understanding from earlier. right? It's like a jigsaw puzzle, right? Our pieces fit करना शुरू कर देते हैं, करते हैं, and then there's another piece that comes in. That piece needs to be fixed into that big jigsaw puzzle, right? It has to fit in, right? And often क्या होता है कि आप fit करने की कोशिश कर रहे होते हैं, and the back you see, and that's a jigsaw puzzle, by the way, right? That's a 1,000-piece jigsaw puzzle that we make every year, me and my son. Okay, so what you do is with jigsaw puzzles, okay, I mean you've fitted pieces and then you put in another piece, and you sometimes found that this is not the right position for this new piece that I'm putting in, right? So but sometimes what happens, you find out that the previous piece laga hua tha wo asal mein theek nahi tha, agla wala theek tha, right? So this is the same with, I mean, your learning as well. I mean, there's some things that you know earlier and then some things you know later. I mean, you should try to fit in the things that you know later with things that you know earlier. Sometimes what happens is you're going to find out that the pehle mujhe samajh aayi thi cheez wo sahi nahi thi, aur jo nayi cheez hai usse meri purani cheezein zara zyada clarify ho rahi hai, and vice versa. Okay, so you try to keep on continuously doing this, especially with this course. Okay, any questions here before I move? Okay, so this is the sifting property. Now, why is this beneficial? That's what we want to do next. I mean, this sifting property may seem like a waste of, I mean, why are we doing this? I mean, so this is why we're doing it, right? That's the next section is going to try to explain why the sifting property is important, okay? Now, so the next section here is, remember, we're dealing with LTI systems, okay? Now, LTI systems are characterized by linearity and they're characterized by time invariance. What our objective here is, or perhaps a goal here is that we need some sort of a description of an LTI system. If I know that description, that is all in all, I mean, completely characterizes the behavior of an LTI system. Does something like that exist for LTI systems or not? And that's what we're headed for. Okay, to give you let's say, I mean, if you're considering a simple amplifier kya karta hai? Okay, there's an input and there's an output, and the amplifier, all it does is it takes the input, multiplies it by some constant, and gives you the output, right? In order to completely characterize all systems which are linear amplifiers, what is the only parameter that you need to know which completely characterizes that system? क्या चाहिए होता है उसके लिए? एक एम्पलीफायर को कैरेक्टराइज करने के लिए क्या चीजें चाहिए होती हैं?
सर वो कोई स्केल होता है जिसके हिसाब से वो लाइक उतना वो करता है,
right? Scale or the gain, right? Exactly, yes. Hassan, right? So the amplification gain, and if you knew the gain of an amplifier, that gain is all that you will need to completely characterize those amplifiers, right? Similarly, what we want to figure out is if given a class of systems which are LTI systems, what completely characterizes LTI systems? That's what our objective is, right? So this new section or subsection is representation or characterization of continuous time LTI systems. So that's what we want to do next. All right. So, I mean, turns out that that's something that completely characterizes the behavior of an LTI system is called the impulse response, right? And that impulse response is defined as follows. Okay, let h of t be the output of an LTI system when the input is a unit impulse, x of t equals delta t, right? So h of t, therefore, is called the impulse response. Why is it called the impulse response? Because it's the response that you get when the input is an impulse, right? That's why the name of the term impulse response. Okay. Now, it turns out, as we're going to see, that the impulse response is, in fact, that's something which completely characterizes the LTI system. In other words, for any given LTI system, if I give you the impulse response, that impulse response is enough, is enough of an information to know each and everything about the system. कि वो memoryless है या नहीं है, stable है या नहीं है, is it causal or not causal, and so on and so forth. Anything that you want to know, how would the output behave when for any given input. Okay, so here's how. I mean, here's a mathematical understanding of why h of t is enough. So I know that if delta of t is an input to an LTI system, the output is h of t, right? That's from the definition. Okay, the output that I get when delta of t is input is going to be h of t. What would be the output when I input delta t minus tau? What would that output be? Remember, this is an LTI system, right? So this is LTI, and this is LTI. In other words, this is the properties of time invariance are satisfied, and the property of linearity is satisfied. So if delta t is the input, the output is h of t. If delta t minus tau is the input, what would the output be? G Masna?
Sir, h of t minus tau.
H of t minus tau, right? That's because of time invariance. Time invariance says that any shift in the input results in the same shift of the output. Okay. Now, what if I multiply the input with x of tau? What should the output be? Remember, this linearity is satisfied. G Mustafa Siddiqui. Mustafa, can you hear me? Okay. I shall multiply by x of tau. Good. All right. What if I integrate on the left-hand side, right? Or integrate the input with respect to tau. What do you expect the output? What should happen at the output? What should happen at the output? G Masna?
X of tau.
X of tau out. So you see, input पे मैंने integrate किया है, तो output पे भी क्या करना चाहिए मुझे?
Integrate ही करना चाहिए.
Integrate करना चाहिए. Why?
Because linear है.
Because of linearity. Remember, linearity says that if there's any linear combination in the input, the output is also going to have the same linear combination, right? And integral is linear, right? It's just that we've seen that that's a summation, right? And so the integral at the input is going to result in the integral at the output. Now, from here, what do we see at the input? The input, as we've seen, is nothing but x of t, right? From the Sifting property. I mean, that's what we know. And from here, we have that characterization. If x of t is the input, what is going to be the output? The output is going to be this y of t, right? And this is the mathematical relationship that is governing the input-output relationship, right? So this is x of t as an input to the LTI system. If that's an LTI system, which has an impulse response h of t, the output is going to be this convoluted looking expression here. Minus infinity to plus infinity, x of tau multiplied by h of t minus tau d tau. Right? So I mean, we've come up about this derivation or this mathematical derivation, and we figure out KG, any input that I gave you, I will be able to find out what the output is for that input if I knew the impulse response. And if I knew the impulse response, the output y of t is going to be given by as a function of x and h through this relationship, or through this convoluted looking expression, right? And because it's a convoluted looking expression, I mean, that's why, perhaps not exactly why, but this operation is called convolution, right? This integral with this shifting at tau and t is called the convolution operation, okay? Right, so this is called convolution integral. And we can basically say, okay, given any input, x of t, the output can be determined through the convolution integral. There appears to be some delay. Okay, and we have some notations here. So we say that y of t is equal to x of t, and we use a star here, star operator, which is not a multiplication operation, right? This is not a multiplication operation, but rather called the convolution operator, right? So this is called convolution operator, right? And this is going to be, the definition here is the following. So minus infinity to plus infinity, x of tau, h of t minus tau, d tau. And I'm going to come to some intuition behind this. I mean, what does this actually mean? I mean, this equation, what does this equation mean? Okay. Right, so Hassan, I don't know what that is. Perhaps we can have this discussion offline. As you say yourself, this is a side question, so we can have that on the side. Okay, Acha. So what I want to do before I give you the intuition, I want to just manipulate this equation a little bit more, and that will perhaps give you a better intuition, right? So, and let's say this is equation 1. So this is equation number, I think 3, because we used 1 and 2 earlier, right? So let me use a change of variables, and let me say v equals t minus tau, right? If v equals t minus tau, if that's a substitution I'm making, and just simple calculus, I would find out that when v, or when tau equals minus infinity, what happens to v? Munim, what is v when tau equals minus infinity? Munim, Musa?
Yeah, so it's t plus infinity, I think.
Plus infinity, right? And when tau equals plus infinity, v equals minus infinity.
Minus infinity.
Because of the minus sign, right? And similarly, just like we did earlier as well, dv equals minus d tau, right? So using this substitution in 3, we have, so using this substitution in 3, what we have is y of t is integral from plus infinity to minus infinity, and this is x of tau, and tau is just simply equal to t minus v, and then this is h of v, and this is dv with the minus sign, right? because of which this is minus infinity to plus infinity h of v x of t minus v dv. And v is nothing but the name of a variable. Let me just use tau instead of v because those are the two variables we've been using. So this is minus infinity to plus infinity, and this is h of tau x of t minus tau. Right, so I have two alternate definitions, equivalent definitions of this convolution integral, which are as follows. I'm going to box them here. So conclusion is y of t is equal to the output of any LTI system is given by this expression, minus infinity to plus infinity, x of tau h of t minus tau d tau, and this is equal to minus infinity to plus infinity h of tau. Both are equivalent. D tau. Okay. Right. So how much time we have? All right. So we take it. This is this is 3 and this is 4. Okay. Now let's talk about some intuition. What this represent? I mean, in terms of practical systems, I mean, what does this impulse response mean? And more importantly, given the impulse response, when you're computing the output through this equation, I mean, asal mein ho kya raha hai physically? Okay. So that's what I'm going to try to focus on next. Right, so some intuition behind 4. So we're going to be dealing with 4 mostly, because I think that's more intuitive. Okay. Right. So let me set the stage up by considering an acoustic channel. Right. Acoustic channel ka matlab kya hai? There's a Hassan, can you unmute yourself and ask me?
Yes. So in the previous case, it was us going over tau, which was going over the delta function.
Yeah.
In this case, we're doing the reverse, right? So we're going over the signal instead.
Yes.
It should still be the same thing.
Yes.
Right. Yeah.
So
I didn't see anything different.
It turns out they're both the same, right? So in एक में आप जो है h को flip कर रहे हैं, as we're going to see. The other one you're flipping x, but it turns out, as we see mathematically, both turn out to be the same because the integral is from minus infinity to plus infinity. Okay, and that's why mathematics is so important. Everything is consistent. So you've been able to mathematically figure out कि आप x को करें या h को करें कोई फर्क नहीं पड़ता, right? But so let me try to give you some intuition. I mean, some maths and intuition go hand in hand, right? So here's some intuition. So if I give you an acoustic channel, what do I mean by an acoustic channel, by the way? Right? So I would consider that channel to be a box, right? And I'd say that there's a speaker or a person who's speaking from one end of the room, and there's a person hearing that speech at the other end of the room or some other point in the room.
Sir, could you explain the convolution again? So how does it work? We like take, how does it work exactly?
So we're not there yet. I mean, how does it work? I mean, we're getting there, Ahmed. Abhi to, we're just given the expression, we're going to work with this expression. Okay. All right. So if there's an acoustic channel, okay, and what that means is that there's a speaker and then there's a listener, right? And the simplest model that I can give you for that acoustic channel is the following. Okay, if there's the input is x of t, which is an acoustic wave or an acoustic signal, right? The simplest model I can give you is that the wave travels in a line of sight from the input or from the speaker to the listener. Okay, and this is y of t. But there is another path, and that is because of reflections that you have in the physical environment. There is another path, which is an indirect part. The wave goes here and then goes back. Okay, so that at the end of the day, this is where a summation occurs. I mean, this is where the two copies end up merging together. They end up adding together. Okay, so this is where this is a summation. Okay, so mathematically, I mean, for this very, very simple model, I mean, this is, I think, called a two-ray model as well. What should the output be as a function of the input? Can somebody try to take a guess? Okay, how would you relate the input and the output? Forget about LTI functions for now, right? दो paths हैं, एक path है और दूसरा path है, जो कि आखिर में add होती हैं चीजें काफी, right? So what should the output be, y of t mathematically? Abdullah Ali?
Ji sir.
What do you think the output should be?
Y of t.
I mean, how should that be related to x of t? I mean, what should the wave experience?
सिर्फ फर्क नहीं पड़ना चाहिए, दो paths हैं, I mean y of t तो same रह रही है.
दो paths हैं, okay. So Ibrahim, देखिए दो paths हैं, and the acoustic wave travels right over the medium. Right, if it's traveling from one point to the next, I mean, is it going to reach the end immediately, or is it going to take some time to get there?
So the time तो लगेगा.
Time लगेगा, right? And that time would depend on the distance it travels and the speed of the sound. It depends on the temperature as well, right? So there will be some delay, right? Is that delay going to be the only thing? Masna, you raise your hand.
Sir, I also wanted to say there will be a delay because it will be reflected, so it will take more time.
Right. So there are exactly. So there are two paths, and each of the paths have different delays because the lengths of those paths are different.
Yes, sir.
Right? And moreover, each one of the paths may also experience different attenuations because the strength of the signal that is transmitted or spoken is not the same as the strength of the signal that is received. I mean, the sound waves actually dampen out because of the medium. Right? आपको करीब आवाज ज़्यादा आएगी, दूर जाते जाएंगे आवाज कम होती जाएगी because of attenuation. Right? So y of t is going to be equal to, as somebody points out in the chat box, Hassan did, right? So this is going to be x1, which is x of t minus t1, some delay. And then let me just multiply it with some constant c1. All this c1 does is it perhaps attenuates it with some factor c1, right? And c2, another copy of x, which is obtained after a delay of t2 seconds, right? So what you receive at the speaker or the listener is x of t minus t1 plus x of t minus t2, a delayed version, right? Both of them are delayed. Okay? And this, by the way, is what causes इस delays की वजह से क्या होता है? I mean, how are echoes generated? How are reverberations generated? Any ideas what reverberations are? No idea what reverberations are? Kyun, Musa? Have you heard about echoes?
Yeah, yes, sir.
Echo
I think
किसने
reverberations would be if it like rebounds off the walls, the sound waves, and then you hear them a second time.
Yeah, so and because the reason why you get an echo or reverberation is because when you get it a second time, it's after a delay. It's not exactly when you get the first time. Okay?
Yes.
So what you know of from high school or for perhaps I mean 9th or 10th, or I mean this is perhaps when you studied this in physics. I mean you're mathematically now expressing it with these delays, right? With a very general mathematical, with a nice elegant mathematical expression. Okay? There's a delay on the direct path, which is t1 seconds. There's a delay on the indirect path, which is t2 seconds. The direct path experiences an attenuation c1, and the indirect path also experiences an attenuation c2. And most likely c2 is going to be greater than c1, smaller than c1. Okay? Because the attenuation may be larger. ठीक है जी तलहा?
Sir, in this case, usually what happens is कि अगर दो sounds आ रही हैं, we can listen to them separately. So shouldn't the waves interfere in a way कि we just hear one overall उनका एक a totally different sound? Interference नहीं होना चाहिए.
Remind me of this as I conclude this section. Okay, I have that point in my mind. Okay, I'll come back to this. जी मसना.
Sir, the signal reflect or the signal that's reflected, so it will lose energy after reflecting from a surface, right? क्योंकि वो उसको भी transfer करेगी. तो उसकी attenuation ज़्यादा होगी as compared to the direct signal because it's reflected.
Yes, typically that's why I said that C2 in general would be smaller than C1.
Thank you. Okay, sir.
Okay, so the attenuation here experiences C1, the attenuation here is C2, and typically C2 would be smaller than C1. Okay, Acha. And if you go back to our previous class and practice problems there, you can verify that this signal that you see or this system that you see, right, where the input-output relationship is given by this expression, is actually an LTI system. This is linear and this is time invariant, right? So all of the things that we've talked out above would hold, right? All of that analysis should be valid, okay? Now, let's try to fit this intuition into that analysis. The first thing is, I know because, so take it for a fact, right? Or other words, one can verify that the system is LTI. Right? So I would let you do this on your own, right? So this is perhaps an exercise, right? What is the impulse response? What is the impulse response for this system? I mean, if somebody were to ask you, yeah, this is the input-output relationship, find for me the impulse response for the system. What would be the impulse response? क्या ख्याल है? Right, Daniel. Okay, good. So Daniel, why are you using H? How? So can you unmute yourself? How do you define the impulse response?
Sir, जो output था ऊपर definition से.
नहीं, impulse response is the output when the input is delta. Right, that's the definition of the impulse response. So in order for me to determine the output or the impulse response, all I'll do is I'll just replace X with delta. Right, so this is going to be C1 delta T minus T1 plus C2 delta T minus T2, right? Because impulse response is defined as the output that you get when the input X of T is equal to delta of T. So I just plug in delta of T in this expression here, right? And I'll get the impulse response, okay? Let me just try to now verify कि यार जो मैं okay, so y of t is integral from minus infinity to plus infinity h of tau x of t minus tau. I just want to see कि यार ये expression ठीक भी है या नहीं है, right? Expression ठीक भी है या नहीं. So all I'm going to do is I'm just going to replace h of tau with this equation 5, right? So this is going to be minus infinity to plus infinity c1 delta tau minus t1 plus c2 delta tau minus t2 times x of t minus tau times d tau, and there's a bracket here. There's a bracket here. So where's that bracket? Here's what the bracket is. Okay, and if I expand this, so this is c1 minus infinity to plus infinity. This is delta tau minus t1 times x of t minus tau d tau plus c2 minus infinity to plus infinity delta tau minus t2 times x of t minus tau d tau And you can verify very easily from the sampling property of the impulse function that we've done. This will indeed turn out to be equal to C1 equals x of t minus t1 plus C2 x of t minus t2, right? So everything is consistent. So I mean, what we've actually verified is कि यार वो जो definition ऊपर दी गई है ना, I mean, that makes sense. I mean, so you're getting the same output. So this is just a small verification, right? Now here's a question. The question here is, okay, what does this? So remember, y of t is equal to the convolution definition by Dick Krauser. This is h of tau x of t minus tau t tau. And for this case, if h of t was the following, you had an impulse at time t1 and you had an impulse at time t2. And this was of height c1, this was of height c2, right? What does these impulses mean? And this may be time 0, right? So this would be h of t. I mean, if I look at this impulse response, what does this tell me? That tells me that this height or this impulse residing at time t1, which is of height c1, actually represents what? Represents कि यार जो output में input की क्या contribution है? Input की t1 delay के बाद c1 amplification हो जानी चाहिए, attenuation हो जानी चाहिए, right? And then there's another copy of the input in the output, and that copy is delayed by t2 seconds and attenuated by c2. Okay, so this is what the impulse response actually means, and this is relevant, or this is visible from this equation as well, right? If you just closely observe what this equation is, this says that the output is a linear combination of shifted and scaled input copies, right? मुख्तलिफ delays के साथ, मुख्तलिफ attenuation के साथ add होके output मिल रही है आपको, right? And this for this particular example where there are only 2 delays, this was a delay at t1 seconds and there was this a delay at t2 seconds, right? And the output is the input delayed by t1 multiplied by c1 plus the input delayed by t2 multiplied by c2. That's what the output is. Okay, so there's some sort of memory in the system, right? And this impulse response indicates what that memory means or what is the nature of that memory is. Ji Hassan.
So I think the intuition में थोड़ा सा मसला है.
Yeah.
In equation 5, we have C1 times delta t minus T1, right?
Yeah.
But that delta function at T1 shoots up all the way to infinity.
Yes.
How does multiplying it by a finite number give you this finite peak instead?
So you're not multiplying, Hassan. You're not just multiplying. You're multiplying and then integrating.
Okay.
Okay. So when you're integrating a unit impulse, even though the magnitude is infinity, the area turns out to be finite. That's why we define the unit impulse to be so infinitesimally small, of infinite length, but a finite area. Okay. So multiplication infinita, integral finite. Okay. Now, so once again, so this Hassan, you still have a question? Okay. So once again, what this represents is this: if I were to give you an LTI system for which the impulse response looked like this figure 1, what this would have meant was कि यार output में input की 2 copies शामिल है. एक copy t1 second से shift होती है और c1 से attenuate हो जाती है. दूसरी copy t2 second से shift होती है और c2 से attenuate हो जाती है. And then both copies are added together, and that's how you get the output. Right, so it's through a linear combination somehow of the inputs. Okay. Now here's the question: are true acoustic channels like that? I mean, would there be finite number of paths for the wave? As I speak in a room, right? The acoustic wave is going to get to you not just from a finite number of paths with finite number of delays, discrete number of delays, but rather infinite number of paths here. Would that make sense? I mean, if there's a path right from this point, there's going to be another part right from their point, right? So the actual attenuation and the delays has to be a continuum of values. Does that make sense? Right? So going by the same argument, if I therefore give you an impulse response, which looks something like this, which is 0 here, and then looks something like this. When you look at this, what do you infer from it? Right? Now there are no longer two discrete paths in the system, but rather a continuum of paths, right? Each one of those continuum of paths experiencing a different amount of delay. And for each particular delay, for example, for this delay, the attenuation is going to be given by whatever this value is. For this delay, the attenuation is going to be whatever this value is. And the number of delays are not discrete, but rather a continuum of values. Because the number of delays are not discrete, but rather continuous. Okay, does that make sense? And this decaying trend, as Hassan points out, rightly so, indicates the fact that the attenuation decreases as the delay increases. Right? So system में memory है, past की values जो है, because delay से आ रही है, past की values output की current value पे affect करती है, लेकिन बहुत ज़्यादा past वाली values बहुत कम contribute करती हैं to the output. Right? And this is what a typical impulse response is going to look like, right? And by the way, this is the impulse response for RC circuits as well. I mean, we have a capacitance के अंदर memory होती है, right? But that memory is sort of decaying in the sense कि जो बहुत past में input आई थी, I mean, the capacitor is not able to hold that value too much. I mean, that is a decaying, as you may be familiar with already. Okay? Now, coming back to one of the points, so this is the intuition behind what this impulse response is going to represent, right? There was a point by, I think, Ibrahim, you raised that point about कि वो copies add होती हैं और discrete echo नजर आता है या एक तो interfere करना शुरू कर देती हैं. Who raised that point? Okay, so if I give you the following impulse responses. Oh, Talha did. Okay. If I give you the following impulse responses, right? Here's what the first impulse response looks like. So I'm almost done. Apologies. So this is h of t, right? And this is what the impulse response looks like, right? So this is this, and it says 0, and then there's a sudden versus another option. And here's what you get. Okay, and let's assume that both of them are for the acoustic channels, right? What do you think दोनों के दरमियान में, दोनों systems के दरमियान में क्या फर्क है? I mean, practically speaking. Talha?
So in the first one, two signals have they're not overlapping.
Yeah, they're
but
not.
But in the second one, there will be some overlap.
Yeah. So what would you expect with this when in a practical setting? I mean, if there's an impulse, there's a system here, system 1, which has an impulse response looking like this, and there's a system 2, which has an impulse response looking like that. So I mean, what if, right? So system 1 और system 2 के दरमियान में क्या फर्क है?
System 1 में हमें एक ही तरह का output बार-बार थोड़े-थोड़े देर के बाद मिलेगा, and system 2 will get a different output through time.
Okay, good. Right. So Ibrahim, you want to say something? So you're on the right track. You say first one is the echo.
जी सर, I think वो first one में एक ही pattern repeat हो रहा है third time के बाद, तो इसलिए वो एक echo की तरह हमें नजर आएगा. और second one तो एक simple एक आएगा और उसके बाद बंद हो जाएगा.
Okay. Right.
वो simple एक.
So you're right. First one is an echo. That would be like, for example, if you're on mountains, ठीक है, पहाड़ पे चढ़ जाएं, you speak out, And what you hear is actually an echo in the sense that you speak, right? And you hear your own voice. And then after a while, you hear your own voice again, right? And the delay between the first hearing and the second hearing is quite a bit. And that's why it's called an echo. That's called an echo. कि आपको distinct copies उसकी सुनाई देती हैं of the same speech, right? So for example, you say out your name, you'll hear your name after a while, right? So after the first copy is ended. Okay, that's called an echo. On the other hand, system 2 is sort of a reverberation. जिसमें आप बोल रहे हैं और अभी आपके बोलना complete नहीं हुआ था before the reflection start coming in, right? So that there's a reverberation effect. Okay, and that's what you add in audio anyway. So to make it sound more appealing, right? What you add in audio are actually reverberations, not echoes. Okay, Ji Hamza.
सर सिस्टम 1 आप कह रहे हैं कि एको है, लेकिन सर एटेन्यूएशन दोनों की डिफरेंट नहीं होनी चाहिए क्योंकि टाइम डिफरेंट है दोनों का.
Right, excellent, right? So perhaps this is a better representation. ठीक है?
Sorry, sir.
Right? But the point is, the point I want you to, the take home is, what does this impulse response really represent? It represents some memory of the dynamics of the system. Past की values जो हैं, वो current output को किस तरह affect कर रही है, right? And on the time axis that corresponds to the memory. And the y-axis on impulse response corresponds to the attenuation that particular delay is going to experience. Okay, that's what is impulse response means. And this is from this expression. I mean, if you look at this expression, यहाँ से भी clear हो जाना चाहिए कि ये क्या बता रहा है आपको. Right? X of t minus tau is being attenuated by h of tau. And then you're taking tau from minus infinity to plus infinity. Okay, so I'm going to stop here and just leave you with a small something to think about. What if, so this is system 3 today. So this is an exercise which I'm going to ask you. System 3, and the CP is going to come into effect from Friday. So if you have an answer to this, you'll get points for that. So this is this system. What does this system 3 does as opposed to system 1 and system 2? That's something I want you to think about. Okay, so I'll stop here. Are there any questions? Jitalha.
So my question was, just like we were talking about sound waves. So
yeah.
If there are two people speaking at the same time, the signal is of same type. Why don't they just interfere and create a new signal so we hear a completely different thing instead of normally we can hear two people speaking at the same time, whatever they're saying.
Okay, good. So Talha, all of these scenarios, you should try to fit these scenarios into the language that we're talking about, right? So the scenario that you're referring to has two speakers. Right? So therefore, there are two inputs to a system. Okay, that's a multi-input system. I mean, we are not going to, as far as this course is concerned, we're only going to stick with those systems in which the input is just one and the output is just one.
Yeah. So, but we in case of just one input, if we add reverberation to it.
Yeah.
So since the first input is still coming in and we start getting the reverberation उसमें add होना शुरू हो जाती है.
Yeah.
So if a person is if the input is the sound of C.
Yeah.
And reverberation as the sound of B, they should interfere and make a new sound instead of we hearing both of the sounds at once.
Okay, so typically, these delays do not change the nature. So remember, these are just delays, right? और delays क्या करते हैं? Delays जो हैं उसमें उसकी shape को change नहीं कर रहे. So the C after a delay will still sound like a C. Right? So you're adding C on top of C.
No, but if the input में now it has obviously input थोड़ा सा आगे हो गया.
Okay, so you're saying कि जी अब मैं B बोलना शुरू कर रहा हूँ और वापस C आ रहा था.
Yeah.
Right. So that may be distorted. So
Okay.
what you would be getting is a B plus C sort of a thing, and you may not be able to correctly hear what the speaker is trying to say because of that distortion, and that does happen.
Okay, so
It
yeah, no,
can happen.
yeah.
It can happen.
Okay.
Okay. I can maybe perhaps put up some MATLAB code in which I do these reverberations and see कि जी reverberations add करने से speech में क्या फर्क पड़ता है.
I think
question.
Talha, you finish first and then I can.
Achha. So I think like I've experienced this in electronic systems. यहाँ पर like over the हम speaker पे बात कर रहे हैं तो yes there is this problem. But if we are talking face to face तब ये चीजें इतनी ज़्यादा तब इतना वो we can differentiate.
बिल्कुल. Excellent. Because when you're talking face to face, I mean, there's not a lot of reverberations. There's not a lot of echoes, right? And even if there are, the dominant path or the line of sight path is the dominant path. So बाकी सारी reverberations are negligible compared to the dominant path, right? So the impulse response for that system is going to be a single impulse.
ठीक है.
ठीक है. लेकिन जो आप इलेक्ट्रॉनिक सिस्टम से बात कर रहे होते हैं उसमें there's feedback की वजह से I mean when you're speaking that your speaking goes into my microphone and that creates the echo because it takes a while for the audio to go from here to there and then through the internet to get to you. That's where you hear echoes. That's called acoustic echo and it's called line echo, by the way. Okay. So all of these mathematics basically governs whatever happens in practice.
Thank you.
Okay, Ahmed, you had a question, I think.